is lesson 2.5, factoring the factor and remainder theorem. You will learn to use the remainder theorem to evaluate a polynomial function at x is equal to c, and you also use the factor theorem to determine if a binomial is a factor, and use that by a factor to completely factor a degree 3 polynomial. So let's begin by first going over the remainder theorem. The remainder theorem states that if a function is a polynomial and is divided by x minus c, then the remainder is the value of f of that value of c. So in other words, if I have this function f of x and I'm dividing it by, let's say, x minus 3, I can evaluate my function at f of 3 by getting the remainder of this division right here. So that's what our remainder theorem is stating here. And the technique that we use it, instead of using long division, we can use this synthetic division to evaluate the function, which is referred to as synthetic substitution. So let's look at an example of this. Let's say we have this function here, and I want to evaluate the function f of negative 3. So to evaluate f of negative 3, what I'm doing is the following. I'm trying to evaluate the function at negative 3. So the normal and long way of doing this is to substitute in negative 3 in for every value of x. So negative 3 to the 4th plus 8 times negative 3 to the 3rd plus 12 times negative 3 to the 2nd minus 7 times negative 3 and then minus 14. Doing this the long and original way, this way right here by substitution, by normal substitution, we would get that the value is going to give us negative 20. But we can get that answer, and again, I'm doing it already, I'm doing all the work for us, but normally I would have to raise this to the 4th power, this to the 3rd multiplied by 8, this to the 2nd multiplied by 12, multiply this with negative 7, and then add and subtract all of these numbers together, and that's going to give me a total of negative 20. I can get that solution a lot quicker by using, again, the synthetic substitution. So by evaluating f of negative 3, what I'm doing is I'm getting this function, f of x, and I'm dividing it by x plus 3. So using synthetic division, where I use the numbers 1, 8, 12, negative 7, negative 14, and a negative 3 out here, I bring down my first number, multiply and add, multiply and add, multiply and add. Sorry, that's negative 3. So it becomes 2, multiply and add. This number is the exact same value as the y value when I plug in the 3 in for all the values of x. I get the exact same answer. So using this technique gets me the answer in a quicker and more efficient way. But again, the catch to this is that this only works again with polynomials. So let's look at a second example. So here, to evaluate f of 1, I want to plug in 1. The normal and old way is to plug in 1 in for every value of x, raise theirs to the respective powers, multiply them by the respective coefficients, and then add and subtract all of those numbers together. And that's going to give us 11. That would end up giving us a total of 11. This method to evaluate f of 1 using this remainder theorem, the synthetic substitution, simply puts a 1 on the outside, so what I'm essentially doing is getting this function of f of x and dividing it by x minus 1. So using synthetic division, this right here, I can figure out that value I can figure out the value of this function at 1 by identifying what the remainder is. So add, multiply, add, multiply, add, multiply, add, multiply, add, and I get 11. So you see the value of my function when x is equal to 1 is going to equal to 11. And there you go. This is your answer. Now this is more applicable and again to some real world situations. So when we have a polynomial function modeled in a real world scenario, like in this example right here, the number of tickets sold during the Oakdale High School football season can be modeled by this function, which is a polynomial, where x represents the number of games played, and obviously y is going to be the number of tickets. So use the remainder theorem to find the number of tickets sold during the 7th game of the season. So x is going to be replaced with 7. So we want to figure out what f of 7 is. So using again synthetic substitution, I can figure out that value by multiplying and adding, multiply and adding, which is 23, multiplying 23 with 7, that's 161, and adding it is going to be 229. So there's our answer, 229 tickets after 7 games. Or during the 7th game. One more example like this. On this example, you're going to notice that again, we're looking again at identifying t. First of all, let me read it. T is the measured in times, and d of t represent the distance in feet of a person that's going to go and travel on a snowboard. So since we're looking for the distance after 1 minute, we're evaluating d at 60. Now you'll notice that we have 0.6 to the second power times t to the second power plus 10 t to the first power, and we're missing a constant. So because we're using division, even though it's synthetic division, we need to make sure that we always have a place for every number from the degree again to the constant. And since we're missing the constant power, we're going to put a 0 for that placeholder. So let's put the 60 on the outside. That's 36. And then multiplying 46 times 60, that's equal to a total of 2760. And there's our answer. So this is the benefit of knowing the remainder theorem and evaluating polynomials. So it just makes it a lot quicker and easier to figure out the solution of the y value to a polynomial given the x value. Now, what happens if the remainder is 0? In those type of situations, then we rely on what's called the factor theorem. Now, if a polynomial function, again, has to be a polynomial, has a factor of x minus c, if and only if, again, the remainder is equal to 0. In other words, again, that if I use synthetic substitution, I get that the result is going to be 0, meaning that the last term, the remainder, is in fact equal to 0. That means that this value of x minus c is going to be a factor. It divides your polynomial without a remainder. So in this example here, in order to determine which of these three is a factor to this polynomial, we can use again the synthetic substitution. Instead of using long division, I know that when I divide by x minus 2 using synthetic substitution, that would be a positive 2 on the outside, a 1, negative 6, negative 17, positive 78, and negative 56. If this is going to be a factor, then I should end up with a 0 at the very end. So let's check it out. So 2, negative 4, negative 8, negative 25, negative 50, positive 28, positive 56, which again is equal to 0. So that means that this is in fact a factor. So this one is a factor. Now, now to check if x plus 7 or x plus 4 is a factor, instead of doing it from the very beginning, we have now a smaller and shorter polynomial to look at. There's no difference like as if this. Look, for example, with some numbers. Look, if I have 24 and I want to see if 6 is a factor, then 6 should divide 24 without remainder, and it does, okay? Now, if I want to check if 2 is a factor, instead of getting 24 and dividing it by 2, I can get this answer of 4 and divide that by 2, which again is going to be 2 without a remainder, divides without a remainder. So since 2 divides 4, that means that 2 also divides 24, because again of how these work and how factors work. So with that idea, I'm going to apply this concept to this here, and instead of starting over and using again the original polynomial, I'm going to use this new factorization and check if 7 is going to be a factor. So this is 7, 3, 21. This is 4, negative 4, and negative 28. Yep, and it is also a factor. This is also going to be a factor. And I can continue checking again with the last one. If I want to check that the last one is a factor, instead of again starting, because this is going to become 0, instead of starting again with this one or even the original one, I can now check this right here and check if the last one is going to be a factor. So since 7 was a factor of this, then it means it's going to be a factor of this one as well. And to check if 4 is a factor of this, I just simply have to check now if 4 is a factor of this. So 1, 4, 7, and 28, and it's not. This is going to give us positive 24. So because this last number was not a 0, that means that this last one is not a factor. So there you go. This is how you use the factor theorem in order to determine if a binomial is a factor of a polynomial. So let's use this idea now to completely factor a degree 4 and a degree 3 polynomial. So let's look at this example right here. So here we want to determine the factorization, the complete factorization of this polynomial. Now, from the fundamental theorem of algebra, since x is raised to the third power, there has to be 3 linear factors, 3 things that multiply to give us this polynomial there. We know that one of them is x plus 3. To figure out the other ones, we're going to break this down to a degree 2 polynomial and then use, again, a quadratic technique to factor in quadratics, or the factoring technique to factor quadratics. So here we'll start by using negative 3. The opposite, since it's x plus 3, we use negative 3. 1, 3, negative 4, negative 12. And then start using our synthetic division technique. So negative 3, this is 0, 0, negative 4, positive 12, and 0. So with this, we now have a shorter factor of this, which gives us x squared plus 0x minus 4. And we can factor this polynomial by a difference of squares. The factorization of x squared minus 4 is x plus 2 and x minus 2. So our factors are x plus 2, x minus 2, and of course x plus 3, the one that I gave you at the very beginning, this one right here. And because we know the factors, then we know our zeros. Our zeros are going to be what makes each one of these factors equal to 0. Well, in order to make this equal to 0, x would have to equal to negative 2. In order to make this equal to 0, x would have to equal to positive 2. And in order to make the last factor, in order to make the last factor equal to 0, our value of x would have to be negative 3. So here are our zeros, and here are our factors. Now let's look at this example here. Another example, again, we'll use synthetic substitution. So 1, negative 2, negative 19, and 20. All right. Obviously, since I'm telling you x minus 5 is a factor, we should automatically know that we're going to definitely get a 0 at the very end. So as a result, we now have x squared plus 3x minus 4. From this here, we now have this trinomial of degree 2, a quadratic trinomial. And the way we factor this is by looking for the factors of negative 4 that add up to 3. Since I need to multiply to a negative 4, I know my factors are going to be positive and negative. Now there's two combinations. I can use positive 2 and negative 2, but I know that's not going to work because that's going to add up to 0. Or I can use positive 1 and 4. But this combination, this order, adds up to a negative 3 and not a positive 3. So I just simply need to switch those numbers. I'm going to make the 4 positive and the 1 negative, and there. 4 times negative 1 is equal to negative 4, and 4 plus negative 1 adds up to 3. So this is the factorization. So you see, by using synthetic division and identifying one of the larger, the quadratic factor of this degree 3, I can now use my technique on factoring quadratics to find the other two. So this is, my factors are, of course, the x minus 5, the x plus 4, and now the x minus 1, which means that our zeros are going to be positive 5, negative 4, and positive 1. So this is what we're looking for. Which now leaves us to our last example, example number 8. For this example, you'll see that the coefficient is a 2, but again, nothing changes. We're going to put 7 on the outside. 2, negative 7, negative 53, and 28. And again, since I know that I'm telling you that x minus 7 is a factor, then I know I'm supposed to end up with 0 at the very end, okay? Excuse me, right here, that should be positive 14, so this is 7 and 49. This is negative 4, negative 28, and 0. So by dividing x minus 7, by dividing our polynomial by x minus 7, we now have a quadratic factor. So this is 2x squared plus 7x minus 14, and this is how we find the other two factors. We know one of the three factors as x minus 7, and we'll get the other two by factoring this out. Now for this type of quadratic trinomial, the technique here is to multiply the leading coefficient with this last number right there, which is negative 8. So we're looking for factors of negative 8 that are going to add up to a positive 7. Again, because I need a negative, I know that the numbers have to be different signs. So I need this to be a positive and this second factor to be a negative of that 8. So we're going to use 8 and 1, a positive 8 and a negative 1. That multiplies, these two multiply again to our 8, and they add up to 7. Now, because I multiplied by 2, I need to undo that procedure not by erasing it though, but by dividing by 2. And that's going to give us x plus 4. And since 1 over 2 keeps it as a fraction of 1 over 2, I need to move that to the front. I need to basically multiply by this denominator of 2, which in very simple layman's terms, what I'm essentially just doing is moving this 2 to the front and make it the coefficient of x. So we end up with 2x minus 1. So here are our factors. Which means that our zeros are going to be x is going to equal to 7, x is going to equal to negative 4, and here x is going to equal to positive 1 over 2. Essentially the opposite of this. The opposite of negative 1/2 is positive 1/2. And there you go. There you have your factors, and as a result, you also end up identifying your zeros with that method. So that concludes the examples on this lesson on the factor theorem and the remainder theorem. Again, thank you again for watching. Let me go to the front. There you go, 2.5. Thank you again for watching, and I hope you have a great day. Goodbye.